Ever feel like you're drowning in AI research? Like every day there's a new paper, a new model, a new breakthrough.
It's a lot to keep up with.
It really is. And that's why we do
This
this,
is the deep dive.
right? Where we take one of those papers that maybe you bookmarked or you saw someone tweeting about.
We try to unpack it.
Yeah. And then
It makes sense.
get to the core. Exactly. So for this deep dive, we're taking a look at TransMamba, flexibly switching between Transformer and Mamba. And, we're not just going to like read the app.
Yeah, no.
We're going to go deeper.
We really want to understand the theoretical innovations
Yeah, the core idea.
and the implications for the future of AI.
Exactly. So this paper is really interesting because it's talking about these two kind of dominant architectures in AI right now, Transformers and Mamba. And, Transformers, they're the powerhouse behind all these LLMs that we hear about.
Yeah, the chat GPTs of the world.
Exactly. But they have this problem where with long sequences of text, they get really, really computationally expensive.
Yeah, the cost grows quadratically with the sequence length.
Okay, so like if you double the length of the text, it's like 4 times more compute.
Yeah, which is not good.
Not good at all. So then comes Mamba,
Yeah, Mamba.
which is theoretically a more efficient approach.
Right. Yeah, Mamba has linear computational complexity.
Yeah. Okay, so that means
It's much more efficient for longer sequences.
gotcha.
Duh.
But it's not all perfect sunshine and roses.
Right. There are some theoretical limitations with Mamba,
Like what?
particularly with in-context learning.
In context
Right.
learning.
That's the ability to learn from information within the sequence itself,
Oh, okay.
and also multitask generalization.
Okay, so it's good at some things, but not so good at others.
Yeah, there are trade-offs.
So the big question that this paper is trying to answer is, can we combine these two? Like get the best of both worlds?
Exactly. The authors aren't just interested in a simple hybrid model.
Right.
They want to find a deeper theoretical unification,
Okay.
a framework where you can dynamically choose the best architecture for the task at hand.
Based on the sequence length.
Exactly. Longer sequences, you might want to use Mamba. Shorter sequences, maybe a transformer is better. And this way you can get the efficiency of Mamba without sacrificing the power of transformers.
So how do they actually do that?
So the central theoretical innovation is the idea of unifying transformers and Mamba in a single framework.
Okay.
And they do this through two main mechanisms.
2 mechanisms. Let's hear it.
The first is the concept of shared parameters.
Shared parameters.
Yeah. So instead of having separate parameters for the transformer and Mamba,
Okay.
they use a single set of parameters that can be used for both.
So like the same parameters can be used for the attention mechanism in the transformer.
Exactly. The QKV matrices.
And also for the state space model in Mamba.
Yep, the CBx matrices.
That's really interesting. How is that even possible? Like those seem like pretty different things.
Right. But there's been some really cool theoretical work recently showing that attention and state space models are actually more closely related than we thought.
Oh, really?
Yeah, there's a deeper mathematical connection between them.
Oh, okay.
And there's even been some empirical work showing that you can transfer knowledge between these architectures.
Okay.
So the authors are building on this existing work to show that you can actually have a single set of parameters that can be used for both.
Wow, that's a pretty big deal.
It is. It suggests that there might be a more fundamental way to think about these models, that they're not as different as we thought.
Right. So shared parameters is one piece of the puzzle. What's the second mechanism?
The second mechanism is called dynamics,
Okay.
and it's all about deciding when to use the transformer and when to use Mamba.
Makes sense.
They introduce these things called TransPoints.
TransPoints.
Yeah, these are specific points in the sequence where the model can switch from transformer mode to Mamba mode,
Okay.
or vice versa.
So the model can be like, okay, I've seen enough of this sequence. I'm going to switch to Mamba now.
Exactly. And this allows the model to be really flexible and adapt to the specific characteristics of the input.
So theoretically, if you have a really long sequence, you might have more TransPoint
Yeah, you might switch to Mamba earlier on in the sequence.
to take advantage of that linear. This is really cool. But I'm thinking, okay, you're in the middle of processing a sequence and you suddenly switch from a transformer to Mamba.
Right.
Doesn't that cause problems? Like, how do you make sure that the information flows smoothly from one to the other?
That's a great question. That's where the memory converter comes in.
Okay, the memory converter. What is that?
It's basically a bridge between the transformer and Mamba.
Okay.
It takes the output of the transformer.
Like the key and value matrices.
Exactly. And it converts them in format that can be used by Mamba.
So it's like a translator.
Yeah, that's a good way to think about it.
And this conversion, it's lossless, right?
Yes, that's really important. They've shown that you can theoretically convert the information from the transformer to Mamba without losing any important details.
That's amazing. So you're not losing any information when you switch.
Nope, it's all preserved.
So we've got the shared parameters, we've got the dynamic switching, and we've got the memory converter, all working together to create this unified framework.
Exactly. It's a really elegant solution.
It is, but now I'm wondering, how do you decide where to put these transpoints? Like, is there a strategy to that?
Yeah, so the placement of the transpoints is determined by something called transpoint scheduling.
Transpoint scheduling.
And this is a crucial part of the whole system.
Okay, so it's not just random.
No, no, no. It's a very deliberate process.
So what are the rules? How do you decide where to put these transpoints?
So there are three main principles that they outline in the paper.
Let's hear them.
The first is that the transpoints should be placed close to the optimal switching point.
Optimal switching point.
Yeah, so there's this point in the sequence where it becomes more efficient to use Mamba than the transformer.
Because of that linear complexity?
Exactly. So you want to place the transpoint close to that point.
Okay, makes sense.
The second principle is that the transpoints shouldn't be too concentrated in one place.
Okay,
So you don't want all the transpoints to be at the same token index,
right.
because that could create a bottleneck.
Gotcha.
And the third principle is that the transpoint schedule should be informed by empirical observations.
Okay.
So they looked at existing hybrid models.
Models that combine transformers and Mamba.
Exactly. And they use that knowledge to inform their scheduling strategy.
So they're taking the best of what's already out there.
Yeah, they're building on existing work.
I like it. So in the paper, did they use a specific transpoint schedule for their experiments?
Yes, they did.
What was it?
They used a cyclical schedule that repeats every 8 layers,
Okay.
and the transpoint value increases logarithmically.
Logarithmic.
Yeah, so it starts at 0, then goes to 128, then 256, and so on.
Up to 8192. So it's
Yeah.
like a gradual transition from transformer to Mamba.
Exactly.
That makes sense. And they also have this formula in the paper for calculating the FOBs,
Yeah, the floating point operation.
which is a measure of computational cost.
Right.
And the transpoint value is a part of that formula.
Yeah, it's a key factor in determining the computational cost.
So you can actually use the transpoint to control how much compute you're using.
Exactly. It's a really powerful tool.
It is. Now, one last thing about the transpoints. They talk about using different schedules for training and inference.
Yeah, that's an interesting idea.
So you could train the model with one schedule
And then use a different schedule when you're actually using the model.
to fine-tune it for a specific task,
Exactly. You could optimize for speed or accuracy.
depending on your needs.
Yeah, it's really flexible.
Okay, so we've talked a lot about the theory behind TransMamba. Now let's talk about the results. Did it actually work?
Yeah, the results are really impressive.
Okay, good. Tell me more.
So they tested TransMamba on a variety of different tasks.
Like question answering, reading comprehension.
Yeah, all the standard NIP benchmarks.
And
And it outperformed all the baselines.
all the baselines. So like pure transformer models,
Yeah.
Mamba models,
Yep.
and even hybrid models.
Even hybrid models.
Wow, that's huge.
It is. And they also tested it on a benchmark specifically designed for long sequences
Okay.
called Long Bench V2.
And
And it blew the competition out of the water.
so it really does work well with long sequences.
Yeah, the memory converter really shines in those situations.
That's great. Now, what about efficiency? Did they actually see those gains in training time?
Yes, they did.
Okay, by how much?
They saw reductions of up to 25%.
25%. That's pretty significant,
That's a big improvement.
especially when you're talking about training these massive models.
Right. It could save you a lot of time and money.
Now, they did say that the actual gains were a bit lower than the theoretical maximum.
Yeah, that's because Mamba implementations aren't as optimized as transformer implementations yet,
Oh, I see.
but they're getting better all the time.
So we could see even bigger gains in the future.
Exactly.
That's exciting. Okay, so they also experimented with different transpoint scheduling strategies.
Yes, they did. What did they find?
They found that layer-specific schedules worked best. Layer-specific.
Yeah, so each layer of the network can have a different transpoint.
Okay.
And they also found that schedules with a broad range of transpoint values worked better.
So you don't want to have all the transpoints clustered together.
Exactly. You want to spread them out.
Gotcha. And they were able to empirically find the optimal efficiency point?
Yeah, for their specific setup, it was around 2048 tokens.
Okay, so that's the sweet spot where you get the best balance of performance and efficiency.
Exactly.
Now, one last thing that I found really interesting is that they got some surprising results when they used different transpoint schedules for training and inference.
Yeah, that was a really unexpected finding.
So they would train the model with one schedule and then test it with a different schedule.
Yeah, and sometimes they would get even better results that way.
Even better. How is that possible?
It's not entirely clear, but it suggests that the model is learning something more fundamental than just the specific transpoint schedule.
So it's learning a more general representation that can be adapted to different situations.
Exactly.
That's really cool. So to wrap up this deep dive, what are the key takeaways?
So I think the biggest takeaway is that TransMamba is a really promising new approach to sequence modeling.
Yeah, it seems like it.
It combines the best of transformers and Mamba.
And it achieves state-of-the-art results on a variety of tasks.
Yeah, it's a really impressive piece of work.
And the theoretical implications are really interesting too.
Yeah, the idea of shared parameters and dynamic switching is really powerful.
And it could lead to even more efficient and powerful models in the future.
Exactly. It's an exciting time to be working in AI.
It is. This deep dive has been really illuminating. I'm excited to see where TransMamba goes from here.
Me too. I think we're just scratching the surface of what's possible with this kind of approach.
And for you listening out there, think about this. What other areas of AI could benefit from this kind of dynamic architecture?
Where else could we see this kind of flexible switching between different approaches?
It's a question worth pondering.
Absolutely.
Thanks for joining us for this deep dive.
And until next time, keep exploring.
And keep learning.